This section is, we're going to be looking at a couple of different types of solutions, and it's not vector or anything like that. It's homogeneous versus particular solutions. I got an example, at least what I think is a very simple example to use to start off this discussion, and it looks like this. Suppose we have this system of equations. All right, if I want to figure out the solutions to this particular system of equations, I'll go to an augmented matrix, and I'll put in my coefficients. Now, since the other side is 0, I'm not going to bother actually making the augmented matrix because I know the other side is 0. So this is good enough for me because no matter what I do, the column that's all zeros isn't going to change no matter what kind of operations I do. So this is an easy example, but it's here to illustrate a point. So let me go ahead and wipe out that -6 underneath the 2. So I'll do -3r1 plus r2. And in case you didn't figure it, it looks like this. So now, since the other side is equal to all zeros, what I have here is an equation of this form. Well, let me go ahead and describe the solutions to such a thing as that. Maybe it might not be a bad idea to rewrite the equation like this. And it's a line, and it's through the origin. If I wanted to write my solutions, they would look like this. All those vectors x, y, where x can be itself, but y is -2/3 x. And let me go one step further. Let me factor the x out so it's now a scalar, and what's left behind is 1 -2/3. Alright, so the solutions look like this. What I want to do is graph these things. I'm going to go pop over to GeoGebra, and let me show you here how it looks. You can actually go, I'm not going to graph the line. What I'm going to do is come back to the vector form. I'm going to have GeoGebra graph this thing, and I want you to see how it does it. So I can simply do this. I can do x times, and then I can put a parentheses, and I can do 1 comma -2/3, and there I get that line. Now, having the fraction inside of the vector is not the worst thing in the world, but it can be improved upon and make things a little bit easier. But before I fix up the vector, let me show you what we got going on here. This line that I drew here, come back to where we were working, is the same as this line right here, y equals -2/3 x. So you can see that x is factored out and times 1 -2/3. But there is one last thing I want you to see. Let me come back here. Let me grab this picture. And I don't need a lot of it, but I need some of it. And I want to grab it and pull it into our discussion. Now watch this. The vector was 1 -2/3. So if you look, here's 1, and right about here is -2/3. If I want a better representation of the vector, or for me a little easier one to work with, if I go all the way to 3, notice that the y value is -2. This point right here is 3 comma -2. And if I put, you can easily see, if I try to keep my thing on there, it's very hard. There's my vector right there. You can see that that vector runs along that line. That means this equals the same thing as this. these are actually saying the exact same things. It's like if x is allowed to be any real number, I can actually factor out a 3 from whatever real number I want and shove it into the vector. So if I multiply both of these by 3, I will get 3, negative 2. I could have done other things if I wanted to. Notice that the vector, if you go in reverse directions here, negative 3, positive 2 is another vector that, if you will, generates the entire solution set. So what happens is this: as x runs from negative infinity to infinity, it will trace out this line. So like when x is equal to 0, it'll just be a dot. And then when x is equal to, I'm using this version of it here, when x is equal to 1, we'll get a dot at 3, negative 2. When x is negative 1, we'll get a dot at negative 3, 2. So as x runs from negative infinity to infinity, those dots fill up this whole line. And so that's how you get a line out of the thing. There's another thing I wanted you to see about this too. If I take the original matrix, 2, 3, negative 6, negative 9, and I multiply it by any vector that is the solution, remember what I can do is factor the x out front. Here x is just working as a scalar. It doesn't have the little arrow above it. So let me continue. And I am going to use the row rule for multiplying the vector, or row vector rule, that's what it's called. So let me go ahead and do that. So the way this works is I'll take this 2 times this 3 and I'll get 6. But then I'll do plus this entry times the negative 2. So that'll be minus 6. Similarly, for the next entry in the vector, I'll take this negative 6 times 3 and get negative 18. And then I will take negative 9 times negative 2 and get positive 18. And that will equal x times the 0 vector, which is just 0, 0. So what that means is any vector here, any vector of this form here, anything that has a 3, negative 2 is a generator, if you will. When I throw it into this, I'll get 0 out of it. So what we have is if A equals 2, 3, negative 6, negative 9, and let's let x equal 3, negative 2, then what I have here is ax equals 0. 3, negative 2 is a solution to the homogeneous system. Ax equals 0. So that's what I want to talk about here. A homogeneous system is one where everything is set to the 0 vector. So now, what I want to do next is compare a similar type of a problem. So here I'm going to do 2x plus 3y equals 12. So now this will be called a non-homogeneous system of equations because it's not equal to the 0 vector. But it is similar to what I was doing before. You see the coefficients haven't changed. Now since I do not have 0, 0 for my answers, I'm going to do an augmented matrix. And notice I'm going to do exactly the same thing I did before. This will be a one-step deal just like before. and I'll get 2, 3, 12, but then I'll get a row of zeros. So I do have solutions. Happens to be an infinite number of them, but look at what I have now. I have 2x plus 3y equals 12. So it's similar to what I had. I had before 2x plus 3y equals 0, but now I have 2x plus 3y equals 12. And so if I wanted to solve for y by itself, I'll do like I normally do. And that is an equation you're quite familiar with in the slope-intercept form of a line. But let me work it instead in terms of vectors. So when I look at my solutions to this system, it has an infinite number of solutions. So let me put that x, y. And what I'll do is I'll go ahead and change the y to negative 2/3 x plus 4. And then I'm going to do a little more to it. This may seem like a weird thing to do, but I have my reasons. I'm going to break that vector up into the following. And then I'm going to go ahead and factor out that x. So I have it broken down. These are the solutions to a slightly different set solution, or a slightly different system of equations. Here, the vector that I'm equaling when all is said and done is 12, negative 36. So look at just the 0, 4, for example. Now I'm going to set a equal to 2, 3, negative 6, negative 9. And let me set an x vector equal to 0, 4. When I do ax, I get 2, 3, negative 6, negative 9 times the vector 0, 4. And once again, I'll use my row vector rule. 2 times 0 is 0, plus 3 times 4. So I have 2 times 0 plus 3 times 4. And then negative 6 times 0 plus negative 9 times 4. And you can see what I get. I end up getting 12, negative 36. So this thing right here, 0, 4, is a solution to the equation ax equals 12, negative 36. So let me write that down. X equals 0, 4 is a solution. There's actually an infinite number of solutions. I didn't have to take that vector. I could actually throw in all of this, and it will still come out to be 12, negative 36. I'm interested in this, though. 0, 4, by the way, is called a particular solution. For those who have had differential equations, you're looking at the same kind of an idea. The homogeneous things turn out to be 0, but the particular ones will be different from 0 usually. So, let me come back here. The set of all solutions to ax equals 12, negative 36 is 0, 4, plus x times 1 negative 2/3. Or, even better, I can rewrite it as this. I happen to like 3 negative 2 better as a vector. So there's my set of all solutions. Now take a look at this. Let me go back to my GeoGebra, and it will actually let me put that in. So I'll start with the 0, 4, and then I'll do plus x times, and I'll do the same thing I had before. I'm going to do 3 negative 2 instead of 1 negative 2/3. It'll amount to the same thing. And let me hit enter. And there's the equation of, there is the line that is generated by that. That means as x travels from negative infinity to infinity, we get this line. Notice that it's parallel to the homogeneous solutions. So the particular solutions are parallel to the homogeneous solutions. Let me grab this thing because I do want to talk about it a little more. And there we have it. So notice these were the homogeneous solutions. And these are the particular solutions. And you can easily see them. Look here. This x 3 negative 2 generated that line. What's different about it? Well, I've got this as 0, 4. Where is 0, 4, you ask? Right here. 0, 4 means I have a vector that starts at the origin and goes up to the point 0, 4. And there you have it. Now, if you take this 0, 4, and let's put that for this, like so. And then if I look at the other one that I had, that one there was 3 negative 2. Look what happens when I add them together. Now, check this out. 3, 2 is what happens when I add the two vectors together. Now, if I start at the origin again and go to the right 3, but then up 2, look where I end up at. I end up at a point on this new line. And that's the way it works. No matter how long of a vector I have, when I add this vector to it, I'm going to get something like this. Remember how we add them? I'll draw a picture to remind you. The picture that we're looking at here is like this. And then when we added these things together, we would create a parallelogram. And then this is the new point that is on that graph. So that's exactly what I did here. If I take this vector plus this vector, remember I make the little dotted line. So I would actually do the little dotted line right here, dotted line. Luckily, there's already a dotted line here, but it happens to be solid. And there you can see. So as x moves, as x gets bigger and bigger, I'll move to the right. That means I'll still have that vector going up directly 4 units, and where it touches is going to be a point on the line. And it will do that throughout. As x goes from negative, well, as x goes to negative infinity, you head off to the left. As x goes to positive infinity, you'll head off to the right. So homogeneous solutions will go through the origin. The particular solutions will be parallel. That's what I'm getting at. So we're going to use the homogeneous solutions to help us get the particular solutions, just like if you have had differential equations, we do in that course. I'm almost done with this example. So this is the homogeneous, hom, and this is the particular, part. Notice every answer so every solution to AX equaled, what was it, 12, negative 36, is of the form, I guess we could call it, yeah, let's just write this. It'll be, you'll have the particular plus X times the homogeneous. So this is what we're going to be dealing with here. General solutions of a system of equations will all take this form. So I want to do some more examples. So this is just to give you a flavor for what's going on in here. Let me give a definition. I mentioned it, but I didn't write it just yet. A system of linear equations is homogeneous if it is of the form AX equals the zero vector. One thing you should note, no matter what, X equal to 0 is a solution if the system, you know what, I should just say that. Let me just stop right there. X equals 0 will be a solution. It doesn't matter if the system's consistent or not. It's automatically consistent because all I got to do is put in X be the 0 vector, then the matrix A times a 0 vector will be a 0 vector. So no matter what, you'll always have that as a solution. X equals 0 is called the trivial solution for obvious reasons. Clearly, we're not really interested in the trivial solutions. They don't do a whole lot. We'll be interested in non-trivial solutions, those times where we have vectors that are not necessarily 0 being the answer. Well, let's go ahead and look at some more examples, and I want to do a little bit more of this stuff in GeoGebra so you can see how the solutions are related to the homogeneuses. So we'll basically just solve, and what are we going to solve? I have x1 minus 3x2 plus 7x3 equals 0, negative 2x1 plus x2 minus 4x3 equals 0, x1 plus 2x2 plus 9x3 equal to 0. So once again, I'm going to go to a faux augmented matrix. I'm not going to bother augmenting zeros because they don't do anything. And let me use my row operations to go ahead and clean up. So I will do 2r1 plus r2 and let's see what we get. Well, I know I cleaned up that entry's no problem. 2 times negative 3. Negative 6 plus 1 is negative 5. And then 14 minus 4 is 10. And then let me go ahead and wipe this item out. So I can just do negative r1 plus r3. Negative 3 is positive 3 plus 2 gives me a 5 in that location. And then negative 7 plus 9 is 2. Now, since the other side is equal to 0, I really don't have a problem dividing out a number if I don't get any kind of fractions. I know the other side's not going to give me a fraction because it's just 0. But before I do any of that, I know right away I can go ahead and take out that 5 in the third row simply by taking R2 and adding it to R3. And now let me divide row 2 by -5. And let's see what we get. Oh, you know what else? I'm going to do 1/12 R3. Okay, let me finish this off. Notice right now, this tells me that x sub 3 equals 0, no matter what. So that one's set in stone. I'm going to do 3r1 plus, I actually meant 3r2 plus r1. And then let me leave the rest of it alone for now. Well, now I can use this one in the bottom corner to wipe out the entries above it. And I can take out this. Well, this tells me now I have x3 equals 0, x2 equals 0, x1 equals 0. So my solution is simply the 0 vector. In this case, it has 3 entries. So for this matrix, I only had the trivial solution. And of course, there's not much more to say to it than that. That's just how the things go. So there's an example of something with a trivial solution. You'll notice that I had 3 equations and 3 unknowns, and that's possible for that to give us a unique solution. It's usually when the rows and columns are not the same, the number of rows and the number of columns, that's when we start to get more interesting solutions. So let me do another one. I want to make sure I got a simple one out like that out of the way. Let's go ahead and try another homogeneous system, and it looks like this. Negative 5x1 plus 7x2 plus 9x3 equals 0. And then I have x1 minus 2x2 plus 6x3 equals 0. So let me pop to matrix notation. Now, one of the things that you might find easier is this one. It would have been nice if that one was up there. And I certainly don't want to divide the first row by -5 because it'll introduce fractions. So I'm going to swap the first 2 rows to put the one where I want it. So the notation I use is this, R1, and I put a little double arrow, like so. R2, that means to swap them. And now I'll go ahead and wipe out that -5. Let me see. 5 times -2 is -10 plus 7. That'll give us -3. 5 times 6 is 30 plus 9 is 39. To simplify things a little bit, I'm going to divide the second row by -3. And then now I'm going to finish off. Right now it is in echelon form. I want to do reduced echelon form to make the answers as easy to read as possible. And also to require no substitution if you do it that way. So to accomplish that, I'm going to do 2R2 plus R1. Let's see. 2 times negative 13 is negative 26 plus 6 is negative 20. And so when I go back to equations now, I get x1 minus 20x3 equals 0. x2 minus 13x3 equals 0. So what I can do then is I can say that x1 equals 20x3, x2 equals 13x3. So x1 and x2 are both written in terms of x3. So what I have then is for my solutions, and here we have an infinite number of solutions. If I call it x1, x2, x3, x1 I'm going to put in 20x3, x2 I'm going to put in 13x3, and then x3 can just be x3. Or even better yet, I can factor the x3 out, and I'll be left with the vector 20, 13, 1. So this is a line in 3 dimensions. You know it's a line because the only variable that I only have one variable. That means that I'm dealing with one dimension, which is a line. If I had 2 variables, I would have a plane. If I have 3 variables, I have a solid. Well, you get the idea. So what we can do for this is we can put this and then just say x3 is free. In fact, x3 is called a parameter. And our solution is in parametric form. Note that you can also write it this way. You could write the solution simply this way. But then just simply let me know that t is any real number. And then I have a version that is that you're more used to calling a parametric one because it has a t in there instead of x3. The name x3 really doesn't mean anything. All I know is that x3 can be any real number, and it will generate, well, in this case, since it's one-dimensional, it will generate a line through the origin in 3 dimensions. All right, so I have a line that goes through the origin. Those are my homogeneous solutions. Now, I want to do the same thing again. I want to give the same system of equations, but instead of homogeneous, let me actually put a vector on the other side. So just like before, this is identical to the previous problem, except the stuff on the other side is not 0, 0. So I'll go to the augmented matrix. And I'll go basically do the exact same things that I did before. Really, you don't do anything different when you've got a column of zeros on the end or a column of numbers. The same steps are there because we want to try to get it into reduced echelon form if we have to. I usually like to go that far to make it clear what the solutions are. So I'll do as I did before. I will swap rows 1 and 2. And then I'll go ahead and clean up as I normally do. And the one I didn't have from before, 35 plus 1 is 36. And lo and behold, I can divide the second row by -3 and I'll be okay. So far, so good. Now, let me go ahead and try to take out this -2 there. And let's see what happens here. Here I'm going to get -26 plus 6 will be -20. And then over here, -24 plus 7 is -17. Now let me go to the equation format. I have x1 minus 20x3 equals -17, and x2 minus 13x3 equals -12. So let me continue this. I'll have x1 will equal -17 plus 20x3. x2 will equal -12 plus 13x3. Now let me write my solutions. And you can see these are infinite as well. So for x1 I had -17 plus 20x3, then I had -12 plus 13x3, and then x3 is just x3. So x3 is our parameter, just as it was before. Now I'm going to change this a little bit to the following. I've just rewritten it. Now I'm going to break it up. Got that. I'll pull the x3 out. And there you see it. This part right here is the homogeneous part. This is the particular part. So this is a P right here, and this is an H. So I'm using H for the 2013 one. So my solution solutions, I should probably say, well, are P plus TH, as before. And you can see it. It would be the homogeneous ones, if we were to go into 3 dimensions, might look something like this. I honestly don't really care. It's not that important to me. But then what we would do is, starting at the origin, at this point right here, add to it the vector that is -17, -12, 0. And so -17, and then negative 12. I guess I'd have to go back this way, because this is x, this is y, and then this is z. 0 is nice, but then I would have like a negative 12, say. So let's do negative 12, negative 17, and 0. So this thing here, I hope I can get it there. And the way I drew, let me get rid of this guy. Well, actually, no, that's fine. Let me go ahead and put it back. That actually was okay. My solutions then are going to be a line that's parallel. Even in 3 dimensions, it'll be parallel. But it will go through this vector right here, the p vector. So there's my particular, and there's my th. And so that's how they're related to each other. If I had 2 variables in the end, 2 free variables in the end, what I would get is probably a plane, and then the homogeneous solutions would be a plane through the origin, and then my solution, any particular solutions, would be a plane that's shifted up. If I were to take a vector and put it right at the origin and project or write the vector starting at the origin, well, at that tip would be where the new plane would be, and then you'd have a plane that would be parallel to the original plane. So in 3D, a plane solution goes through the origin in the homogeneous system, and the particular system, we have the same plane, but shifted p. I just want to leave it at that, because whatever p is pointing at, that's the direction we shifted at. So you'll have, this may be the homogeneous case down here, and then the particular might be something over here. These planes, of course, go on forever and ever in all directions. So this would be the particular, the set of particular solutions. And then if you were to go here, from this point here, the corner, to right here, this point here, that would be our p vector. All right, a little more practice. I have x1 plus 3x2 minus 5x3 equals 0. x1 plus 4x2 minus 8x3 equals 0. Negative 3x1 minus 7x2 plus 9x3 equals 0. And so I'll go to my not augmented matrix. And start performing the row operations and see where it leads us. So I'll do negative R1 plus R2. And I know what I'm heading for here, so I'll put those. And let's see here. Negative 3 plus 4 is 1. Positive 5 minus 8 is negative 3. And then I'm going to wipe that negative 3 out there. So I'll do 3R1 plus R3. So 9 minus 7 is 2. Negative 15 plus 9 is negative 6. Now, of course, when you do have any kind of a non-trivial solution, one of the rows is going to disappear on the original matrix because you have to have one equation is a linear combination of the other equations, or one row is a linear combination of the other rows. So, well, I got a 1 is a nice spot here. I'm going to use that to take out that 3, and then I'm going to take out that 2. And let's see where it leads us. So I'll do negative 3r2 plus r1. Let's see. I know I get that. 9 minus 5 is 4. I have 0, 1, negative 3. And then I'll do negative 2r2 plus r3. 0, 0. Oh, 0, good. Which is what I figured I was going to get anyways. So I have x1 plus 4x3 equals 0. x2 minus 3x3 equals 0. And so my solutions x1, x2, x3 looks like, let me see, x1 was equal to negative 4x3, x2 was equal to 3x3, and then x3 was just itself. Or I'll pull out the x3, I get negative 4, 3, 1. Now I'm going to do the same thing again. Except I'm going to work a non-homogeneous system of equations. And so I'll go this time to an honest augmented matrix. And run through the row operations as far as I need to, just like before. All right, so now let's see here. Negative r1, so yep, I'll end up with a 1 there. And then 5 minus 8 will be negative 3. It's the other side I got to look out for. Negative 4 plus 7 is positive 3. And then 3r1 plus r3, so 9 minus 7 is 2. Negative 15 plus 9 is negative 6. And then 12 minus 6 is 6. And then I'll do negative 3r2 plus r1 and negative 2r2 plus r3. And I see when I do the negative 2r2 plus r3, it's going to give me nothing but zeros, which is good. That way I'll have solutions. And then 1, 0. Let me see. Negative 3 times, so 9 minus 5 is 4. And then negative 9 plus 4 is negative 5. So my answers then, I'll get x1 plus 4x3 equals negative 5. x2 minus 3x3 equals 3. So my solutions look like the following. x1, x2, x3, that equals negative 5 minus 4x3, 3 plus 3x3, and then finally x3 is just x3 at 0. I can write it as 0 plus 1x3. The reason I do that is for what's going to come next. I want to break this up in the following format. -530 plus x3 times -431. By the way, when you solve this, any particular thing, anything can happen here. This could be an x2 or an x1, or it can have more than one variable there, and then you get a plane. But as before, this is nothing more than a line, and then when you add this vector to a line, you get a parallel line. And once again, I'll call this guy right here a particular solution. Actually, this whole collection here is a whole collection of particular solutions. But this guy right here is sort of the leader of those particular solutions. It's the one that we go by because that's the one that I can pull out from here. And of course, I'll use H to be that portion, the homogeneous portion, or at least just the -431. You plug that vector in, A times that will equal 0. Of course, A times this will equal whatever we had on the other side to begin with. To get a little more comfortable with the geometry and the way solutions are generated, let me give you something here. A equals the vector 3, -4, and B equals the vector -2, 5. Now what I would like to do is find a parametric equation of the line through A parallel to B. So first let me graph these things. Move that up a little bit. Let me pop over to GeoGebra to help me with graphing. I had to adjust my B. Let me fix that. The B is equal to, we'll come back here, -2.5. And let's go ahead and pull that thing in. So luckily it labels A and B for me to make it simple. Now we want to go through the point A, so we want to go through this point, but we want it parallel to B. So I need it to go, whatever B looks like, I need it to look like something like this. All right, any vector t times, well, what was B? -2.5 is parallel to B. So as t runs from -infinity to infinity, I'll get a line, and if I don't do anything to it, B will be extended up and down from -infinity to infinity, be line to the origin. But if I want to get another line, so this here, it's not just parallel to B, it is the line generated by B. But if I don't want it to be on B, but I want it to be parallel to it, I'll have to add it to A. This is what I'm looking for. Take a look. Let me come back here. And for this, we put y equals A plus x times B. I think you can use t, but I'm not really sure. Look what I have there. It's exactly what I said I wanted. Oh yeah, I guess throw it in here. So it has what I'm looking for. It goes through A. So through A. And if you look at it, it certainly looks like B and this line are parallel to each other, right? Parallel to be. And that's what you're looking for. And to put in the actual numbers then, A plus TB, that equaled A was, I think it was negative, or no, it's 3 negative 4. 3 negative 4 plus T times negative 2, 5. So, and you can see it from here. This is no different than something like a point intercept formula in regular algebra. You can see it if you will. This is like the M. T is like would be like your M, I think. No, actually, the negative 2, 5 would be like the M. T is like the X since it's the variable. And this is something akin to the intercept point. As T equal, here's how you can tell if you're right. If T equals 0, this piece disappears and you will end up at 3 negative 4. So that's how you know that 3 negative 4 is actually on the line. Now that we've done some of the computations, let's take a look at some of the theory. There is only one theorem in this section, and it goes like this. Suppose AX equals B has a solution. So it may only be the trivial solution, but at least it's consistent. That's what's important, is that the system does have at least one solution. And let P be a solution. So that means that A times P will equal B. Let me put that down there. A, P. When I plug P in there, well, when I replace X with P, I'll get B. The solution set of AX equals B is the set of all vectors of the form P plus H, where H is any solution to AX equals 0. So if I replace X with this H, then I'll get 0. The reason why I don't put a TH here is because I'm not certain that the homogeneous part will be a one-dimensional solution. It may have an S and a T variable involved, and its solution set may be a plane through the origin. So I'll just let H be any vector that satisfies the homogeneous equation. Well, let's take a look at the proof. Let W be a solution to AX equals B. So we have AW equals B. Let H equal W minus P. Remember, P is also a solution, so W is a second solution. Then, when I look at AH, that is A times W minus P. You'll remember I can break this up. There is a distributive property in this world. And I happen to know that this is equal to B minus B, which is the 0 vector. So H is a homogeneous solution. Furthermore, I can do this. W equals W, yes, I want to do that, W minus P plus P. I'll do a little bit better. This equals P plus W minus P, which equals P plus H. So that is what the theorem was saying, was that our solutions would be of the form particular plus a homogeneous. And remember, W was any solution that we could have. So that completes the proof, and I can move on. Little note, same thing as before. If I do A times P plus H, you can see that it's going to be a solution just by AP plus AH. I know that AP is equal to B, and I know that AH is the zero vector. So those are, in fact, solutions. Suppose AX equals the zero vector has only the trivial solution Okay, remember the theory says as long as we have one solution, then we can use the theorem that I had before. Next, let P be any solution to AX equals B. We know the set of all solutions is of the form P plus H. However, the H are the solutions to the homogeneous system, and it only has one because we only have the trivial solution. But that then equals the single vector P. What that means is that P is a unique solution to AX equals B. So if you can get a unique solution, or a trivial, the only solution being the trivial solution to this, then AX equals B will have a unique solution. So we won't have an infinite number of solutions. It'll not only be consistent, but only have one and only one solution. Now, if the vector B does not equal 0, is it possible that the solution set AX equals B is a plane through the origin? Well, I don't know. Let's take a look. Let's let P be a solution. So we know that AP equals B. So one thing you should note, I know that P cannot equal the 0 vector because I'm told that B is not the 0 vector, so I can't have that happening. All right, we know our solution set is P plus H for all possible H's that solve AX equals 0. Now, if the solutions form a plane, we know that H generates a plane through the origin. So we'll have something like this. All the set of H's will give us some sort of a plane. So there might be the origin. Let's call that there. And so since P is not 0, it's going to have some definite length. That means we're going to have a plane that I don't know how much, but let's put P to be this thing. And then I'm going to basically have a parallel version of a plane. Let me see if I can fix it. So these planes would be parallel to each other, and you can see that they'll be separated. So there's no way that this plane can go through the origin. It's actually pushed away. So the answer to this question is simple. No. And one last thing I guess I wanted to show you was sometimes you might end up with a matrix like this, or an answer like, well, let's do it this way. 1, 0, 1, 0. I think this will be the easiest one I can do. Or maybe even more. And I don't know, call these stars like so. So what you're going to end up with a situation like this is that x1 plus x3, let me call it star 1 and star 2, will equal star 1, and then x2 plus x4 equals star 2. So then when you go to write your solutions, x1 will equal negative x3, and then x2 will equal negative x4, plus star 1 plus star 2. And so then when you take a look at your solutions to this x1, x2, x3, x4, you're going to see that I'll replace x1 with star 1 minus x3, and I'll replace x2 with star 2 minus x4, but then x3 will be itself, and then x4 will be itself. And what I can do is the following. I want to do star minus x3. That I want to leave as it is right there. Star 1, star 2 minus x4. And then I want to do 0 minus x3 and 0 plus x4. So I'm at plus. Now let me continue writing this. I'm belaboring a point, I think, probably far too much. The first entry I can do 0 or star 1 minus x3 plus 0 x4. The second one I can do star 2 plus 0 x3 minus x4. And then I can do 0 plus x3 plus 0 x4. And then the last one I can do 0 plus 0 x3 plus x4. Then when I break this up into the following, multiple vectors, I'll have *1, *2, 0, 0 plus negative x3, 0, x3, x3, 0, x3 plus 0, x4, negative x4, 0, x4, x4. I'll continue on. What I'm going to do is leave the stars where they're at. But then, what I'm going to get for the parametric stuff, I'll factor out an x3. And then I'll also factor out an x4 from the second piece. So now what we have here is this is the particular, and then I would let H be the collection of all of these things. These are my H's, if you will. So all of those things, if you were to take any of these things and plug them into the original equation, you would get A times that is equal to 0. And then, of course, if you throw this thing in, you'll get the numerical answer, the non-zero answer that you have for that particular example.